Welcome to lesson 5 on topology. We're going to talk about a few more topological invariants, boundary numbers, and holes, and we'll also talk about subdivisions and connected sums. And at the end of the lecture, I'll put together a little chart that shows the different topological invariants for some of the shapes that we've studied. And just as a reminder, this is our double torus, so that'll come up again in the in this particular lecture. So put it here just as a reminder. It's basically two toruses connected, and there's an open pathway between the two. So the boundary of a surface is a concept that refers to the set of points that mark the edge or limit of a surface. A surface can have 0 or more boundaries. For example, a sphere has 0 boundaries. You can keep going around the sphere and you never hit an edge. The number of boundaries of a surface is a topological invariant, which means if you have a surface with 2 boundaries and another one with 3, then they're topologically different. For example, a cylinder has 2 boundaries, the circles at the top and its bottom. As I mentioned, the sphere has no boundary. Also, the torus and the Klein bottle have no boundaries. And the Mobius strip, if you recall, you can run your finger along an edge and you'll come back to where you started. So that's just the one boundary that you have for a Mobius strip. We have a planar figure here at the bottom of the slide, and this has 3 boundaries. It's kind of obvious. You have one boundary here, another boundary here, and then sort of the exterior is the 3rd boundary. So on the left here we have a Klein bottle. We already mentioned it. It's doesn't have a boundary. So if you take, for example, an ant and it's walking along the boundary here, it would come up to the top and then go inside, then pass through here. Remember, this intersection here only exists in our drawing, but in 4 dimensions this is not an intersection. So the ant would come through, and no matter how that ant tried walking, it would never come to an edge. So there's no boundary for the Klein bottle. And the projective plane also has no boundary. Even though this may look like a boundary, we had this unusual stipulation that when you opposite points are connected. So if you have, again, an ant walking along here, when it gets to A, it automatically comes back to A here, and it could just keep circling. So it never, the ant never hits a boundary. There's no boundary for the projective plane. A surface can be subdivided by adding vertices and edges in such a way as to preserve its Euler characteristic. On the left, we have a pentagon, 5 sides, and the Euler characteristic is 2. That's easy to verify. You have 5 vertices, 5 edges, and 2 faces. And we can subdivide it, as we've shown here on the bottom. And the number of vertices are the same, but we've added 2 edges, so that goes from 5 to 7. And then this was 1 face, and now it's 3. And then, of course, we have to add the exterior as a face. That's the rule for planar objects. Excuse me. And so we get 2 again. So that worked. We preserved the Euler characteristic. Here we have a 3-dimensional object, a cube, and as we've shown before, the Euler characteristic is 2. If we divide this face in half, we get 2 more vertices, so we go from 8 to 10. Number of edges is now, what was 2 is now 4, and then we added this, so that's 3 more edges. We get minus 15, and then we added 1 more face because we divided this in half. So again, we got back to the original Euler characteristic. And on the right, we had a subdivision that didn't work. It's because we didn't actually divide any face or any edge We did add vertices, but you see here the square has Euler characteristic too, but when we stick this triangle here in the middle, we get 3 more vertices, 3 more edges, and we add 1 more face, and so now the Euler characteristic is 3. So this is not a valid subdivision because it does not preserve the Euler characteristic, and the conclusion is that this topological surface is different from this topological surface. There are different types of subdivisions. The simplest one is called triangulation. We'll give you an example as we talk through the details here. So let's start with a hexagon, and we can triangulate it by drawing these 3 edges here. Do you notice we get 4 triangles, and the union of the triangles covers the entire surface. So that's in general true when you do a triangulation. It doesn't have to be planar, but I just took a simpler example here. The edge of each triangle is either a boundary of the surface or shared with exactly one other triangle. So for example, this edge is a boundary of this triangle, and this edge is a boundary also of the surface. But then this edge here is shared with this triangle. I mentioned the second point. The third point is the intersection of any 2 triangles is either empty. We don't have that case in this example here. But if we have, for example, if this solid went up this way, let's say it's another triangle, then this triangle, and let me draw it just to make clear what I'm talking about. Let's just say that this solid was like that. Then this triangle and this triangle would have, or let's say this triangle and the one on the bottom here, their intersection would be empty. Then in other cases, they have a common vertex. So for example, this triangle and this triangle, in fact, all 4 of these share that same common vertex. And then, for example, this triangle and this triangle share a common edge. Okay, so that's triangulation. I should point out that the triangles aren't necessarily flat. I mean, we took a planar figure here, but if you triangulated a sphere, for example, then you would have the triangles would be curved. We use the word triangle in general here to take into that into account. And then in general, you can use any connected graph to do the triangulation. So you can use squares and other shapes, but it's usually easiest to use triangles. And if you're looking for a deeper discussion on this, there's an entire Wikipedia article entitled Subdivision Surface, 2 words, subdivision surface. So you may want to have a look at that. The Euler characteristic is a topological property. If 2 surfaces have different Euler characteristics, then they're not topologically equivalent. Subdividing a surface simply cuts it into smaller pieces, but does not change its fundamental shape, assuming we preserve the Euler characteristic. So we saw the counterexample of that a few slides ago. We have this theorem, which is almost a tautology, because it says for a given surface, all of its subdivisions have the same Euler characteristic, but the subdivisions have to be defined in such a way to give you the same Euler characteristic. We saw an example of one that didn't happen. So the question here is what subdivisions are valid, and that's a bit involved. I'm not going to go into all the details here. I think the easiest thing is just to check to see if you have the same Euler characteristic. That's easy enough to check for an example. And if not, then you know you don't have a valid subdivision. Typically anything inside a polyhedra which doesn't touch any of the edges or vertices is going to cause a change to the Euler characteristic, as we saw with the square and the triangle inside of it. We can use the previous theorem to compute the value of the Euler characteristic of a sphere. In the figure below, the Euler characteristic of a sphere is computed using 3 different subdivisions. So we only needed to do it once, but I wanted to just show that you always get the same answer. You need to be a little bit careful, especially this one on the right. So on the left, we put a subdivision here of the sphere, and again, this is, as I alluded to in the previous slide, this triangle is actually curved, but we still call it a triangle. So you have 2 faces, the interior of the triangle, and then the exterior, basically the rest of the sphere. So f equals 2. Then the number of edges is 1, 2, 3, and the number of vertices is 3. So the sum here, it comes to 2. And in fact, that is the Euler characteristic of a sphere. We do it another way here. We can use something other than a triangle. We use semicircles. So we have this semicircle, this one, and then this one on the bottom. So there's 4 edges, 1 for each semicircle. Number of vertices is just 2 here and here. The number of faces, I've kind of drawn them here. You need to think a little bit about it, but it's kind of a quarter. Each face is a quarter of the surface. And again, you get 2. Then the one on the right is a bit tricky. We put in 2 triangles, and then, of course, the remaining area here. But if you recall, the theorem said we needed to have a connected graph. If you don't use a connected graph, you won't get the answer 2 again. So we need to connect these 2 triangles. Once we do that, we will get the same answer. The number of faces is 1, 2, 3. So we get 3 here. The number of edges, so we get 1, 2, 3, 4, 5, and then another 4 here. So that's 9 edges. The number of vertices is 4, and 4 is 8. And again, you get 2. The Euler characteristic of a point, and therefore also that of a closed or open disk, is 1. The reason is that you can compress, shrink down a closed or open disk to a single point. And in terms of how we view this, for a closed disk, you can think of it as having a single face, the interior and its boundary included, no edges if we treat the boundary as part of the face, which I just mentioned, and no vertices. And then you just get this formula here. So on the top, I have a sphere and a disk not yet removed. So we just have the sphere, and it has Euler characteristic 2, as we've shown. If we go ahead and remove the disk shown here on the bottom, then we get we just have to subtract the one face. So we have one face less than here, and we get 0 minus 0 plus 1, and we get 1. So when you remove a disk, it's not just true for this example, but when you remove a disk from a surface, you reduce the Euler characteristic by 1. That's what I've written here. Consider a surface S with Euler characteristic X. Create a subdivision which contains a disk. If we remove the face consisting of the disk, leaving the vertices and edges on the boundary of the disk with the original surface, then the resulting surface has Euler characteristic X minus 1, since we're only removing a face here. And that's a general theorem. Removing a disk or a surface homeomorphic to a disk, a non-intersecting polygon from a surface reduces the Euler characteristic by 1. On this slide, we have an example of the theorem from the previous slide. We have a cube, and we have a subdivision here, not one that preserves the Euler characteristic. We can see that. The number of vertices are the 8 from the cube, and then 3 more, so we get 11. Number of edges 12 from the cube and 3 more. And then the number of faces is the 6 from the cube, and then this is broken into 2 now, so you get 7. So this has an Euler characteristic of 3, but it's still a valid surface. It's just it doesn't have, it's not equivalent to a cube because of this, the way we subdivided this here. That's not the point I wanted to make here. The point is, if you remove this face, the triangle, then you still have the same vertices and edges from the triangle, but you've subtracted one face, and so the Euler characteristic goes down by 1, which is what we stated in the previous theorem. So I want to talk here about something called a connected sum. What you do is let's look at an example. You have two toruses here, and you can remove anything, make a cut, anything that's homeomorphic to a disk. I did a triangle, but we could have done a circle, a disk, and we remove this, and then we join the two objects, in this case the two tori, along the points here on the two triangles, and we get what's called the connected sum, and we write it this way here. So if we have surface S1, say this is S1, and surface S2, then the connected sum is written this way here with the symbol in between the two, the names for the two surfaces. I'm just restating what I have here. So this is a two-hole torus, and you can have n-hole tori just by doing another connected sum, and we'll see that this is part of the classification theorem in the next lesson, but I just wanted to kind of introduce you to the concept of connected sum first. So it doesn't have to be tori, it could be any two surfaces could be connected in this manner. The Euler characteristic for the connected sum of two surfaces is the sum of the two Euler characteristics minus 2. We can prove that. So let's say we have surface S sub 1, and we have the vertices, edges, and faces here, V sub 1, E sub 2, F sub 1, and we include the vertices and edges of the face to be removed in this count. And then we do the same thing for S sub 2, and further assume that E equals V. So the number of vertices equals the number of edges related to the face to be removed. So for example, if we remove the triangle, then we would have 3 edges and 3 vertices. So this would hold for that. When the two faces are connected, the two V vertices on the two faces to be removed are joined, leaving V vertices. Similarly, the two E edges are joined, leaving E edges. This is after we do the connection. The two faces are gone after the merger, because now you just have a hole between the, you pull the faces off that are being removed, then you just have a hole between the two surfaces which you connect. And so what we get, just write it down here. So the number of vertices is what we start at V1 and V sub 2 and minus V, because we had 2V before we did the connection procedure. And the same thing here. We just add the vertices here and then minus E from this. And then the number of faces is 2 less, because we basically removed the two faces when we did the joining. So let's continue this on the next slide. We're almost done. We just need to plug all this into the Euler characteristic formula. So let's carry over where we left off from the last slide. And if we plug these into the V minus E plus F formula, we get this. Then we have V1, V sub 1 minus E sub 1 plus F sub 1. We get that. And then we get V sub 2 minus E sub 2 plus F sub 2. Then we get a minus V minus E. And then we have the minus 2. But remember, we stated that V equals E in our assumption. And so we've shown that after you remove a hole from the two surfaces and then connect them together, the Euler characteristic is minus 2. So if we kept, for example, if we kept connecting toruses, we would keep subtracting 2 from the Euler characteristic, and we would go off to minus infinity if we wanted, if we indefinitely connected the tori together. As we stated on the previous slide, an n-hole torus has Euler characteristic 2 minus 2n. And sometimes we use the shorthand where we say if n equals 0, then you have what's basically a sphere. So a torus with 0 holes we call a sphere. That makes it a little bit easier to write things in terms of symbol terminology. So here we have T hash sign n is the symbol for n tori connected together. And as I say, if you have n equals 0, then that's a sphere. The number of holes in a closed surface is called the genus. I should have said closed surface here. The connected sum of two spheres is again a sphere. You can just think of two spheres, cut a hole or a disc in both of them, join them together, and then you can just expand the hole out and smooth things out to get one sphere. If you connect projective planes together, you get an Euler characteristic of 1 plus 1 minus 2 equals 0, and you can keep doing that. So if you connect n projective planes, you get 2. The Euler characteristic is 2 minus n, and the symbol here, excuse me, the symbol for n connected projective planes is p hash n. The genus of a surface is basically the number of holes, and it's typically defined for closed surfaces like the sphere or the torus. You can extend it in some cases. We're not going to do it here, but I'll just mention it. It can be extended for surfaces that are not closed by capping them off with a disc and then saying that they have the same genus as the surface created after capping it off. So if you capped off a cylinder with 2 discs on the top and the bottom, you could say that it has 0 holes like a sphere and make the genus of the cylinder 0. But again, we're not going to pursue that approach here. So here we're going to talk about genus for orientable, I should say closed surfaces here. As I mentioned on the last slide, we're going to focus on the closed surfaces with respect to genus. So the equation for closed orientable surfaces is the Euler characteristic equals 2 minus 2 times the genus. G is the genus number of holes. So for sphere, we know there's no holes, and so we just put a 0 for G, and then we get 2. We already computed that to be 2, but this is sort of another way of getting it. For the torus, we know we have 1 hole, and the Euler characteristic is 0. And again, we've computed that in a previous lesson, but we're just showing that it fits this formula. Then a double torus, which has 2 holes, you plug that in here, and you get minus 4 from 2, and you get minus 2. So each time you add a hole, the G goes up by 1, and of course the Euler characteristic goes down by 2 since you're subtracting -2 times the genus. The genus for non-orientable surfaces can be defined. It's a bit tricky. I'll talk through it a little bit here, and then I'm going to point you to some videos and another website to get more information. But let's just go through a first level of detail here. So you have a similar formula. It's the Euler characteristic equals 2 minus k, where k is the non-orientable genus, and that's counting the number of things called crosscaps. A crosscap is a topological construction used to describe non-orientable surfaces. Intuitively, it represents a region on the surface where orientation is flipped. In other words, where you go from clockwise to counterclockwise. And recall our lecture on orientation. Adding a crosscap to a surface means modifying a surface by cutting out a disk and then gluing the edges of the whole back together in a twisted manner. Such an addition makes the surface non-orientable. So that is not an obvious statement, or what this looks like is not at all obvious. We'll put some information in the information to this video. There's a fairly nice web article that talks about the crosscaps, and then there's a couple of videos. I prefer one over the other, but I'll give you the link to both of them, and it shows you what the crosscap looks like. But it's sort of the idea is you're basically cutting a hole, a slit in a surface, and you're inserting a Mobius strip in there. So you're creating the non-orientable part. And depending on how many of those you need to add, that gives you the genus. So I'm just going to state this here. I don't think these are obvious either, but just for your information, the projective plane is equivalent to adding a single crosscap to a sphere. And in your k equals 1 in that case, and your projective plane, as we know, has Euler characteristic 1, so that works out. The Klein bottle is equivalent to adding 2 crosscaps to a sphere. So making 2 cuts and adding 2 Mobius strips. And in that case, your non-orientable genus is equal to 2 because you have 2 crosscaps. So again, this is a lot to take in. I'll give you some links to, if you're interested in digging a little bit deeper into what this means. But there is a way of, the point is there is a way of defining something like a hole for non-orientable surfaces, and that's this thing called a crosscap. So I've summarized some invariants for different surfaces based on what we've been talking about over the last few lectures. So let's go through this. We have a sphere, a disk, a cylinder, a torus, a double torus, a Mobius strip, a Klein bottle, and a projective plane. So we've seen all these before. The first 5 here are orientable. So if you take, recall our little figure where we had something like this when we talked about orientability, and we can move that anywhere we like on any of these surfaces and come back to where you start it, and it would still have this orientation. But if you do that, if you take this type of figure, a Churl figure, and you move it around a Mobius strip or a Klein bottle or a projective plane and return back to where you started, you're going in the opposite direction. So I drew that kind of badly. Let's try that again. So we going that way, or vice versa. So the idea is when you go through that area where you flip orientation, That's the reason why you're not orientable. So we have that. We have a genus. So I mentioned that we're not going to talk about the genus for things that are not closed. So the disk is not closed. The cylinder is not closed, obviously. The Mobius strip is not closed. So I'll just put a check mark or a dash in here. Then the genus of a sphere is 0. There's 0 holes. Torus, 1 hole. The double torus has 2. And then we just talked about in the last slide that the non-orientable genus, this cross cap, you need 2 of them for a Klein bottle, 2 of them in a sphere to get a Klein bottle, and 1 for the projective plane. The Euler characteristic, we've computed these before. I won't torture you with that. We've already done those. And then the boundary number of the sphere, of course, has no boundary. Disk has 1. Cylinder has 2, 1 on the top and the bottom. The closed figures like the torus, the double torus, they don't have any boundaries. The Mobius strip has a single boundary, and then the Klein bottle and projective plane are also closed, so they don't have any boundary either. So the point here is, if you look at these different topological invariants, you would expect them for 2 topologically equivalent surfaces, that every one of these 4 things would be the same. And you can see here that that's not the case. There's always something different between any 2 of these. So if you picked the Mobius strip and the disk, they have different orientation, they have different Euler characteristic. The only thing they have in common is they have the same boundary number. And we can go through the list here, pick any 2 and they're different. Okay, so that's the end of this lesson. There's one more lesson related to surfaces where we talk about classification, and we have most of the pieces that state that general theorem. That's a short lecture, but it's important because it ties together a lot of what we've been doing up to here.